Hello students, welcome to the course Network Theory. In the previous few videos, we have discussed the first part of the module 1. So the topics like source transformations and star delta transformations. And also we have seen the problems. So in the second part of the module 1, we will be discussing basically loop analysis and node analysis. Okay. So first we will consider the loop analysis. Okay. So also called as mesh analysis. Okay. So what and all we discuss here is we'll apply the mesh analysis to linearly independent voltage sources for DC networks. Okay, so first part we'll consider all DC networks. In the end, we'll see the AC networks. Okay, in DC networks, we'll take one by one. First, if independent voltage sources is there, how we do? Independent current sources are present, how we do? Voltage source, dependent voltage sources and dependent current sources are there, how we solve the problem. Then finally a concept of super mesh. Okay, so then after that we'll take the mesh analysis. Okay, together. Sometimes all these type of problems also will be merged and it will be a complex problem. Okay, so like this we'll categorize this mesh analysis into different topics, and another next 3 to 4 videos we'll be discussing completely about mesh analysis. Okay, so today we'll see the first one, the independent voltage sources. Okay, so before that, so just we try to generalize the theory part of this mesh analysis. Okay, and how basically we'll write a mesh equations. Okay, that is very important. Once you know how to write the mesh equation, you can give any problem, you are able to do that. Okay, so then based on the topic, little bit variation will happen in the mesh equations, but first thing is a basic network is there given, how to draw the or how to write the mesh equations. So that is our intention. Okay, so we'll introduce mesh analysis. A closed path or a loop. Okay, a closed path or a loop. Okay, so which you call closed path? So circuit with, okay, starting point end. So this is a loop, closed loop, right? Closed path, there is no path is open. Okay, so if this is open like this, okay, so it is a open circuit. Clear? Is drawn starting at a node and tracing a path such that we return to the original node without passing an intermediate node more than once. You should not travel more than once. That is called as loop. A mesh is a special case for a loop. In the basic circuit terminologies, we have mentioned this difference, loop and mesh, right? A mesh is a loop that does not contain any other loops within it. Okay, so we have taken a circuit like this, right? In the basic circuit terminologies. So this is called as a mesh. This is called as a mesh. Okay, so once you call this as mesh, so you could not call it as loop. Okay, so whereas loop can contain any number of meshes. So this outer one, we can together we can consider it as loop. This we could not consider mesh because it is already having two mesh. Okay, this is the concept of a loop and mesh. Okay, that's why terminology will use, sometimes we'll call loop analysis, mesh analysis. Okay, so both it will come. Okay, the current flowing in a mesh is defined as mesh current. Okay, so mesh analysis we are doing, mesh network will say, or mesh current will say, equations we call mesh equations. Okay, everything about mesh. As a matter of convention, the mesh currents are assumed to flow in mesh in the clockwise direction. Okay, so normally that will not be given, so we'll assume clockwise. Okay, accordingly we'll solve the network. Okay, so first case we'll consider mesh analysis with independent voltage sources. Okay, so that means you have a resistive network in DC. We are considering DC. That means you have a resistive network, and in between you will have the voltage sources. Okay, independent means you will have the circle symbol. Clear? We employ, so in this case we may employ KVL around each mesh. Okay, so each mesh you will apply a clockwise direction KVL. So previously also you have done, same way we are doing. We'll travel around each mesh in the clockwise direction and sum the voltage rises and drops encountered in that particular mesh. Okay, so voltage rise when will happen? Then when there is an energy source, right? Okay, or in general notation we'll say, if minus plus is there, we'll say energy rise. Plus minus, if it is encountered in when you are calculating, we'll consider drop. Okay, we will adopt a convention of taking voltage drops to be negative and voltage rises to be positive. So when we are using this convention, drawing in mesh equation, So voltage drop, okay, that is plus minus. If it comes, we'll write it as minus. Okay, minus plus if it comes, we will consider plus. Okay, when we are writing the equation. Okay, so this is the idea. For more things, for the given network, mesh equations are written and the mesh currents are calculated. Okay, so how many number of meshes are there, that many mesh equations you will get. Then using the calculator, okay, so complex equation mode you have, right? So there you can select which, how many equations are there. Okay, one equation is there, straight away answer will come. Two are there, two equations will come, two currents will come. Three meshes are there, three equations, three currents will come. Four meshes are there, four equations, four current will come. Okay, so this is the basic idea. Once the mesh currents are known, the branch currents are evaluated. So once you come to know the mesh current, that means this complete mesh you come to know in a network, then you can easily calculate the mesh current, branch currents. Branch current means this is one branch, this is one branch, this is one branch, this is one branch, right? Each branch there may be element connected or may not be connected. So with respect to that, branch currents also will be calculated. Okay, mesh currents and then all the branch voltages. Okay, once the mesh currents are known, the branch currents are evaluated in terms of mesh currents, and then all branch voltages along with branch voltage also we can calculate using the Ohm's law. Okay, V equal to IR. Current in this branch, you know, resistance you multiply, you'll get the branch voltage. Okay, so that is the idea. So this is the different way they can ask the problem. Okay, just they can tell you to find the mesh currents, or they can ask the branch currents, or they can ask the branch voltages. Okay, so it will apply both to mesh analysis as well as node analysis. Okay, only the technique is different, both are network. Okay, if we have n meshes, this is what I told you, how many meshes are there, that many equations will be there. Okay, then n mesh currents will be there, and you require n independent mesh equations. Okay, so this set of n equations are independent and thus guarantees a solution for the n mesh currents. Okay, each equation is different from another in a slightly manner. Because of that, you will get a unique solution. Clear? So this is the idea of a mesh analysis, and that is to with the independent voltage sources. Okay, so if you have this independent voltage sources, so we will see now, okay, example network and how to write the equation. So this one equation, so instead of writing R1 R2, I have written in terms of Z, because we are analyzing with respect to AC also. Okay, so Z means impedance in AC network. So this Z is given as R plus J into X. Okay, it will have a resistive term along with reactive terms. So this you have gone through basic electrical engineering, right? So if reactance is not there, that means inductor capacitor is not there, so then you will have it is a resistive network, right? So normally in DC network you don't have reactances, that's why we'll call it as resistive. But for general analysis, I have considered it as element Z. Okay, so don't confuse with that. So you have a voltage source here, E1, Z1, Z2, Z3, Z4, Z5, and then here E2. Okay, so these are planar network you have. Okay, so three meshes are there here. So or three loops, we say loop 1, loop 2, loop 3, or any order you can write, no issues. Okay, so now as I told you, if you have three meshes, what we need to calculate here is the current I1, I2, I3 in this case. Okay, so you could not calculate using a direct Ohm's law here or any other law. Okay, so KVL we are applying, but KVL is just write the equation. Okay, but after that we will be applying the mesh analysis, right? So this is a concept of mesh. Okay, so now three equations we need to write for that. Okay, so how we write that? One way is you can write using normal KVL, Kirchhoff's voltage law around the loop. Okay, so another way is general equation we can write. So that I have written here, I will show you in the second part. But first we'll try to understand with applying Kirchhoff's voltage law itself. Okay, so very simple. Now you have here minus plus, and there is normal element is there, you will have normally voltage drop plus minus. So this is plus minus. Okay, so how you can write this? E1 minus, this is a plus, right? Minus plus E1, this is a voltage drop. So how you write the voltage here? Current is I1 in this mesh and Z1. Okay, so you can write this as I1 Z1. Next I have Z2, but this Z2 element is not belongs to only mesh 1, it is belongs to mesh 2 also. That's why, so here the current will be calculated as, so here current direction is like this, okay, whereas here current direction is upward. That means they are opposite. So how you write? I1 minus I2, because with respect to mesh 1 we are writing, so mesh I1 minus I2 into Z2. Okay, so that's what it is, also minus, okay, minus I1 minus I2 into Z2, okay, which is equal to 0, because sum of voltage drops and voltage rises is equal to 0 according to KVL, right? Now I have simplified and written directly here. Okay, so this is I1 Z1, here it is minus I1, so when I split it outside it will be minus I1 Z2 plus I2 Z2. Okay, this is equal to 0. Okay, so from this, sorry, I1 Z2, right? Okay, plus I have to write, sorry, this is plus not minus here. Okay, this is plus here outside, so E1 minus I1 Z1, okay, minus I2 Z2. Okay, so this is minus here, here we have to write I2 minus I1, I2 minus I1. Okay, so there is little bit confusion here. Okay, Z1. Okay, so it is correct, previous one only correct, so I will try to erase this. Okay, so here it is E1. Okay, so as it is, you write as Kirchhoff's voltage law, I1 Z1, then minus only, it is voltage drop. So I1 with respect to I1, first loop we will write I1 minus I2 Z2 is equal to 0. Okay, so then what we will do, we will take the current terms right side, so then you will get the I1 Z1 minus I1 Z2 plus I2 Z2. Okay, when you take right hand side, so this becomes minus here, I1 is having two terms Z1 plus Z2, that is grouped together and written here. Okay, and I2 Z2 equal to E1, this is the first equation. Same way you can write the second equation also. So you have here, this will be written here from here. Okay, so here I will consider plus minus in this loop, this is again plus minus, this is again plus minus, there is no voltage source here, all voltage drop only. So this is written as minus, okay, here I2 minus I1, because here plus minus is there, so it is like this, and here current like this. So with respect to mesh 2, now I2 minus I1 Z2. Okay, you can take all plus also, all minus also here, because all are voltage drop now, that's why. Then this is with respect to this loop only, that's why it is I2 Z3. Then this loop is with this and this, so I2 minus I3 current and this Z4, because this branch current is here subtraction of these two current. Okay, I2 minus I3 Z. When you simplify this, okay, same way what I done here, so you'll get minus Z2 I1, then Z2 plus Z3 plus Z4, Z4 I3. Okay, similarly if you write last equation, okay, so you have minus Z4 I2 you will get, because it is this current. Okay, I3 minus I2 will come. Okay, there is no I1 current here, right? So even in this equation I3 was not there, but in this equation I3 came, so I3 is not there means here it is 0. Similarly here I1 is not there means it is 0. Okay, so 0 into I1 minus Z4 I2 plus Z4 plus Z5 I3. So two resistance you have and E2 will be there. So here there is no nothing was there, 0. Here it is minus E2, because here now applying KVL like this. But if you consider the direction like this, then would have plus. Okay, so if you are considering this direction, you should throughout you have to consider same. Then this would have come minus E1. Okay, since we have taken clockwise, so it is plus minus, so we have to consider it as minus. Okay, so it will come minus, so it will be E2 plus E2 will come. When you take right hand side, it will become minus E2. Okay, so just solve this. Okay, so this is one way. Okay, so writing this equation, then simplify and then group the I1 I2 I3 terms and write this. So this is a little bit difficult, okay, in all the time. So for that there is a generalized equation you have, but very first you understand with this only. So as you proceed with problems, okay, as you mature with the solution, so what you have to do, you have to learn this method. Okay, this is very simple. what is there here is so mesh 1 is connected with mesh 1 and mesh 2. Mesh 3 is not there. That's why straight away I3 term will not come 0. Okay, this is the one point. Then with respect to I1, all the self resistances, what are the resistances with respect to this loop? Z1 and Z2, that we are adding Z1 plus Z2, and current is I1, and whichever is current in between it will come, so that will come automatically minus sign, minus Z2 into I2 current. Straight away we are writing. So similarly we'll see with second mesh. So here what is the here it is belongs to mesh 1 also, mesh 3 also. You'll get I1, I2, I3, all the three currents. Okay, so what is I1 you will get? So that is Z2 into I1 minus, because it is not self, no, mutual. So mutual always comes minus Z2 into I1, and the self Z2, Z3, Z4, three resistance are there, all three will added into I2. So this is the self. Again you have mutual here Z4, so that's why minus sign, Z4 into I3. So this is the way. Similarly fourth one, so this belongs to only mesh 2, mesh 1 is not there, that's why here it is 0 straight away. Okay, and with respect to I2 it is only this element, right? So Z4 into I2, mutual element, you will get minus current. Okay, so then self what you have, Z4 and Z5 with this. Okay, Z4 plus Z5 I3 equal to minus E2. Okay, so here if you have taken E1, so here it will come minus E2. Okay, so this is about the general, so just I will explain in next slide. Okay, so this way how we will write the mesh equations. So this is a general one. If you may not understand, don't worry, as we solve the problem, so your doubts will be clear. So these are general and mesh equations what I told you. So this is how we write. Okay, this is the self one, Z11 I1. This is with respect to 1 and 2 mesh, Z12. This is with respect to 1 and 3, Z13. Nothing is there, it is 0 came, right? Equal to E1. Next Z21, it is mutual with respect to, this is 2 and 1. Okay, Z21, in this case this is 1 2, 1 2 we are writing here, 2 1. Then it is self. Okay, then it is Z23. So 2 we are there, that's why we will write first 2 then 3. Here 1 was first, so that's why everywhere one term will come first. Similarly 30, so E2 is 0 in that case, but we will consider general E2. Next 3, see here the third set of equation, 3 will come third loop, then 3 with 1, with first loop what relation. Okay, then second loop what is the relation, then self loop. Okay, so this is the diagonal one, we call it as the self. Okay, and all are mutual. Okay, so where here Z11 is equal to, so now we'll describe this. Z11 is equal to Z1 plus Z2 in that equation, sum of all resistances in mesh 1, or it is also called as self resistance of mesh 1. Z12 equal to minus Z2, which is the resistance common to mesh 1 and mesh 2. Z13 is 0, there is no resistance common to mesh 1 and mesh 3. Okay, similar way Z21 also I will tell. Z21 is minus Z2 in that equation, if you have noted down. Resistance common to mesh 2 and mesh 1, as the network is bilateral. Z22 is self resistance of mesh 2. Okay, then Z23 is resistance common to mesh 2 and mesh 3. Okay, so it was Z4 there in that case. Similarly Z31 resistance common to mesh 3 and 1, there is no resistance, so it was 0. Z32 resistance common to mesh 3 and mesh 2, it is minus Z4 there. And then sum of all resistances in mesh 3, or self resistance of mesh 3. Okay, so this is the generalized equation. Okay, so now to solve this equation you have again two methods. Okay, what is that two methods? So before that we will finish it off. The self resistances Z1, Z22 and Z33 are always positive. Okay, so this is the point you can remember. And the mutual resistances like Z12, Z13, Z21, Z23, Z31, Z32, they are all positive if the two mesh currents through them are flowing in the same direction. If I1 and I2 are flowing in same direction, then it is positive. So it is not so, right, in this equation, that's why it is negative. Okay, it may be positive if the current flowing in same direction. Clear? Then E1, E2, E3 are the sum of all EMFs in mesh 1, mesh 2 and mesh 3 respectively. They are positive. How they will tell that positive and negative, you had doubts maybe. Okay, positive if along the direction of their mesh currents. If it is in the direction of mesh currents, we will consider plus. Okay, they are voltage risers, otherwise they are negative. Okay, so it was opposite, right? So in the third equation it was current direction is like this, but it was having plus minus, right? So that's why it is negative. Okay, so don't worry about this. So as you solve problem, it will be clear. So now to solve this equation, there are two methods. One is if you get some three equations now with coefficient values, straight away you can use the calculator. Okay, so you use the mode equation. So select their three equations. So then it will ask A, B, C, D, or A1, B1, C1, D1, A2, B2, C2, D2, A3, B3, C3, D3. All the four values you substitute this coefficient value and click equal to. So you'll get all the three values. First value is I1, second value is I2, third value is I3. So as you are writing the coefficient, okay, if you are writing this first, that coefficient, second this coefficient, that's third this coefficient. So this normally will do in normally DC network problems. Okay, so DC network, so only resistance is there, so no problem will come. So calculator is there and calculators are allowed in exam hall. So that's why it is simple method. Okay, whereas when it comes to AC network, you could not use the calculator there because resistance, inductance, they will come with the J terms, right? It is not possible there. So in that case, we have the another method, that is Cramer's rule. Okay, in mathematics you maybe learned that. So just I will try to highlight that here. So the same equations what we got, that we will write it in a matrix form. Okay, so what is these equations are nothing but the coefficients of I1, I2, I3 with respect to first mesh equation. This is I1 current equation, I2, and I3 nothing was there, 0. Similarly with I2 you had this value I1, then with respect to I2 second mesh, and then with I3 you had all the three values, right? Third mesh you had no I1 value, so it is 0, then I2 value, and then I3 coefficient, right? So this is the coefficient and the currents are I1, I2, I3, and right side you had E1, 0 and minus E2. Clear? So now we will find out the delta, delta 1, delta 2, delta 3. So how many equations are there? That many delta 1s are there. So how to calculate delta? Just you take the matrix determinant of this resistive network, resistive matrix. So take Z1 plus Z2 minus Z2. So how you solve that? You know, right? This coefficient into this matrix, right? So then minus of this coefficient into this row and this row you are selecting. Next plus 0 into these two matrix, right? So this is the way you will solve the delta. Similarly, we will find out delta 1, delta 2, delta 3. What we are going to do in delta 1 is the first row, first column will be replaced by the right side coefficient. Okay, that is E1, 0 minus E2 will be replaced. We will find the new value of delta 1. Similarly, if and keeping remaining same. Similarly, to find the delta 2, so what we will do, we'll substitute this in the middle row and remaining two rows will be unaltered. Okay. Similarly, delta 3 will substitute in this row and these two will be as it is. Okay. So this is how we will find out the 3. Okay. Next, I have done it. So directly I have done here. Okay. So this is the above matrix is nothing but the delta 1. Okay. See here, the first one is replaced with the E1, 0 minus E2 and remaining as it is. Second, this is delta 2. Okay. So delta 2. So here I have substituted the right side values and here these two as it is. Then third one, it is delta 3. See here, substitution is done here and you'll get a new value. Okay. So then if you divide these each delta 1, delta 2, delta 3 by respective delta, so delta you will get the respective currents I1, I2, I3. Okay. So I have here clubbed here. Okay. So delta 1, instead of writing that, I have written directly this matrix determinant divided by delta. Okay. So normally you calculate like this. Delta 1 you calculate, delta 2, delta 3 separately. Then you take this ratio, you will get I2. Then delta 2 by delta will give you current I2. Okay. And then delta 3 by delta will give you current I3. Okay, so handwriting may not be correct. Okay, so this is the way we will solve the problems. Okay, this is about the theory part, how we write the mesh equations in a two way. One is using KVL and simplifying, another is generalized equation, how we write using self resistance and mutual resistance, and then solution. Okay, with respect to DC network, straight away using the calculator we will solve. So with respect to AC network, we will use this Cramer's rule. Okay, so this is mentioned here, Cramer's rule we will use. Okay, So this is it. In the next video we'll solve the problems, okay, and also we'll see the second variety, okay. uh, the independent current sources are present, how the equation reduction will happen, all this, okay. So with this we are stopping here, okay. So go through the video once again, because all new topics it may not be understood in the first attempt only, okay. So you have the option of this YouTube link, so you can over again and again you can play this, so 1 or 2 times you listen, once write it, so you'll understand, okay. Thank you, we'll see in the next video, okay.